Oh, whoa. I love you can really see the delay between some video.
Microsoft PowerPoint, present in Teams. Present. Hello, good to see ya. Sure. Oh, working.
Oh, hi. Hello. I'm reading on the damn stasis spot. Have you played FTL Festival? It's a roguelike game. So you go system to system, you get weapons and upgrade your ship and all that. You guys. Oh, right. Ryan's here.
Can you hear me?
Yes, we can hear you. Can you hear us?
Yeah.
A little bit choppy. Yeah, how do I do that? Oh, is it gonna do the choppy like thing that I did last time because it was so annoying in here? Do we want to try? I hope it's not my computer. Can you go out there and talk for longer?
Can you just start reading?
Just
start monologuing.
Yeah, recite a poem.
Plans.
Yeah.
While we figure out a way to escape the trap.
Start reading the slides.
Hello, can you hear me? This is my critical design review. Sonata I vertical launch rocket plane. Is my audio good?
Do you want to try somebody else's computer? It might be mine.
It might just be. We might just have to.
You think it's the connection? Should we try it?
Yeah. Experiencing technical difficulties. Oh. Yeah. Yeah, try it again though. We're using a new connection. Funny.
This is the critical design review for Sonata I vertical launch rocket plane from Cal Poly Space Systems.
Hold on, we're still connecting. Hold on. Hold on. All right. We're not cavemen. We have technology.
Yeah, go try it.
Hello, testing. Can you hear me? Is it choppy?
We might be doing composite stuff.
I can hear you.
You might just have to do it from your laptop. And then just repeat the question.
Just do it out on my laptop speaker.
Yeah. And the most important person to hear it is the person speaking.
True.
So, yeah. All right, we're just switching to the laptop speakers.
I should have brought like a Bluetooth speaker or something.
This is the critical design review for Sonata I vertical launch. Is this audio choppy?
On the Teams call.
Oh, gotcha.
Thanks. I try now.
Hello, testing. We are not making a missile. I repeat, we are not making a missile.
Beautiful.
It's not a whole.
Yeah, that works. All good. Okay, and then how do I make this big screen? On the, oh, do I have to like extend displays instead?
Yeah.
And then no, it's not doing it.
Oh, let's just. I just had to take out your phone and have the everything.
Oh, presenter mode. Are you recording the meeting? Oh, Will is. Whatever. I don't need to do it if he's already recording. Okay. And then I can just go. Where did I just do that? Share. Window.
You have LinkedIn Premium. You just did LinkedIn.
Oh, I got it.
Sorry.
Okay. Now I should be able to do presenter mode. Content only to that screen.
Gotta get the, what you call it.
Hey, Josh.
Oh my gosh.
There's ridiculous. Oh, hey, that is.
What's up? Can you guys hear us?
Good to see you.
See, hold on, I can't hear them.
Yeah.
Oh, they're muted. That would explain it.
Oh, that one.
If we turn on both mics, we get feedback.
Hold on.
Another meeting still.
Still
Hear me?
Matthew, that Cal Poly.
I think so, yeah.
Can you see the PowerPoint?
Yeah. Try hitting that present, like sharing correct button.
Here?
No, bottom, on the bottom, it's like the one next to
Ah.
the book. Yeah, that one.
Ah, there we go.
Cool. Looks good on our.
Okay. Perfect.
Looks good on your end.
Everybody can hear me? Okay. Well, we should probably get started then. Hello, everybody. Welcome to Critical Design Review for Sonata I, our flyback recoverable booster. I'm going to start here with the agenda. We're going to start with just a little introduction, vehicle overview, and we'll get into concept of operations, and then go into all the fun design stuff. And then we'll give you guys a schedule and get out of here. Introduction, presented by myself. So we're doing multiple test flights. The idea is to test a couple of different configurations with different ideas that we'll go over in more detail in the aero section. But our success criteria that's common to all of the missions that we're going to fly are that we want to reach about 300 feet after a relatively straight ascent. And that we chose because that's about when we'll be at our like double-ish our glide speed so that we can kind of do a maneuver safely and roll back around and start gliding instead of being vertical. And then we want to be able to land the vehicle under wing power.
You have 300 to 400 feet. Is that like, so if you hit over 400 feet, are you gonna be like, that's too high? Or is that upper limit? Do you have an upper limit for a reason? Or?
We are limited by the FAA.
Okay.
To be under 400 if we want to stay as a like class 1 amateur rocket. But I don't know how much of an issue that will be if we're just like launching in a field somewhere.
Right.
The FAA is probably not going to come knocking on our door and
But
murder us.
that 400 is set by something.
It is set by them, yeah. And then there's a couple other constraints too that I think we talked about in the PDR as well, given by the FAA, that it has to be like under a certain amount of weight of propellant, has to be under a certain amount of total weight. And so we've designed it to those. It's under 3 pounds total weight and then under, I think, 300 grams of propellant. And so you'll see that later. And then secondary objectives are just to gather necessary data to tune the flight software. We want to analyze performance of different physical components that we're testing. And then we want to be able to gather data on like the different lift characteristics of our different kinds of wings and make sure that during ascent, it's not going to like tip because our wings are designed improperly. Because if we were to put that on a rocket, we'd then have to generate extra drag by using our active control to stabilize it. All right, vehicle overview. This is our open rocket for it that we use mostly just to get the center of gravity, and then kind of to look at the center pressure as well. It says warning here, thick fins may not simulate accurately. So we're hoping that we can trust that, but we're also hoping to do physical testing in a wind tunnel to confirm it for both the like CG and stability. The idea is that so background on plane versus rocket. Plane, you want your CP to be closer to your CG. Rocket, you want it to be further away because when you're going up, you want it to be further behind. So we're shooting for 1 on the way up and then hoping that it will come back far enough that with the canards, we can kind of cancel out how far away it is from the center of gravity by having canards in the forward, so far forward that we can then like pitch up with control surfaces on the canards when needed to like maintain stability while in flight. But obviously we'll have to do testing of that we're hoping to do in the wind tunnel first and then launch it with the actual rocket once we've confirmed that like we can control it. Here are some fun CAD models. We'll go over all of these in more detail in the subsections pertaining to them, but so you can see, ooh, pretty. And then in case you were worried about how big it is, we have a banana for scale. So you can see how large the vehicle is. We had issues with that where people couldn't tell how large the vehicle was last time, so. Oh, I like how it like puts a shadow in there. That's so cool. It's like, yeah. That's very cool. Oh, sorry, you want to get a picture of that slide? Okay.
Great content.
Okay. Vehicle overview. We covered this in the PDR, but we have some changes here that we'll go over again later. So same as before, while on ascent, the flight software will be configured to maintain our trajectory as straight up as possible. Hopefully we'll be able to just have hands off the sticks, and then ground control station is just observing the video and spotting from just to make sure it's not going to like die. And then electronic systems function as normal, so we'll get telemetry, video feed, data logging, all that. Question?
So this brings up a question. So like, is your flight software going to be able to handle both automatic guidance and then controlled input guidance?
Yeah, so it's not like automatic guidance as much as it is just the stabilization.
Yeah. Oh yeah.
Yeah, just in case anybody is listening, it's stabilization, not guidance. And I think what we're planning on using, I'll talk about in the like flight software slide, is a software called ArduPilot. That's just a firmware you can load on, and there's already like libraries and stuff to support the flight controller that we're using to do all of that automatic stabilization. I'm not sure if it will transfer to like going vertical, so that might have to be like a custom plugin to make sure that it can do vertical stabilization.
I would definitely be careful because like rocket stabilization is going to be a different.
Yeah.
It's a different control problem.
Yep.
It's inherently unstable.
Yeah.
So especially with your configuration, you're probably gonna know, I don't really know, I'm not.
That's why we're testing it. Yeah. That's why we're building the small version that hopefully won't hurt anyone if it crashes.
Yeah, so I'd just be careful also, like, because I think your flight software is gonna get all sorts of.
Yeah,
bad stuff
it will get
if you're
angry.
Trying to.
Yeah.
Automatically control.
Yeah.
Rocket flight.
And that was part of why we chose Ardu Pilot over something like iNav, because it's more customizable and we can write plugins and change parameters and stuff for that reason. Because I'm foreseeing that we will definitely have to do a lot of that. And yeah, and so the idea is that you just have it run the active stabilization in like an upwards mode, and then you flick a switch into the like normal glide mode, and then it uses whatever the normal active stabilization is that Ardu Pilot comes with, because it knows how to do that for planes and I don't. Yeah, and then second mode of operation, glide. Same thing, just human in control now from a remote location, probably in a bunker. And then concept of operations, same thing here, except last time you remember we had a like optional we lose control, parachute deploys. We ran some numbers and we'll talk about this in a later slide, but if we're only getting up to like 300 feet and the furthest away we'll be is like halfway down when we're coming in for a landing, we'll only have like 100 feet to deploy a parachute. We figured that it's not worth it to add all that weight for something that may or may not actually like save the rocket. And we'd rather just kind of put everybody in a safe location. And if it crashes, it's under 3 pounds. It won't damage the tree that it smacks into. So the environment is safe and we will make the humans safe. Yeah, we'll cover it a little bit in more detail. And then, so basically pad idle, we just confirm that we have all the links that we need over radio, confirm that range is clear, declare go for launch, and then ascent. Flight software and control, as I was just talking about, we maintain the upward trajectory until motor burnout, and then we enter the transition phase. So the idea is to coast until we reach a safe airspeed to start maneuvering into glide conditions. And that would be around 60 feet per second, we thought. And obviously we'll have to do some testing of like how fast can the airspeed get before we get unstable in the wind tunnel. Then we go to the glide, maintain under 50 miles per hour is what we're thinking will be safe in order to be able to land it. Yeah, that's what we're assuming. We're obviously we will have to test that because we're not confident in the software fully, or that we were using the software correctly to determine that. And then and also that our manufacturing tolerances are definitely not going to be like exactly what we've designed in the in our models. And then we glide to landing, and then hopefully power down, recover, mission success. Yay! All right, moving into subsystem overviews. Oh, question. Sorry.
Move on. Yeah, I know.
Yes.
Like what exactly?
We have a test matrix that we'll show for the wind tunnels and for launches. And then we'll also talk about further. I have a schedule slide for our tentative schedule, and we'll talk about why it's tentative as well. So we'll go over that. Sweet. Here's our agenda for subsystem overviews. I will hand it over to Kyler for lift surfaces and control surfaces. Thank you.
Do I just arrow?
Yeah,
Okay.
space works too.
Okay, so this is basically the same as PDR right now. We still have the same delta wing design as the old booster. It's the same ratio that we're keeping with for the shape. We decided on 2 wings, so one's gonna be symmetrical, and then we're gonna test a non-symmetrical airfoil just to see if the auto stabilization can control that, which we'll also test with the wind tunnel. Yeah, so I'll show this in the CAD, but basically it's just the same as the old Star booster. The wings placed at the base of the booster for maximum stability, and then canards are ahead of that towards the nose cone. And this is the symmetric airfoil that we're using. This is a sizing chart that I use to pick up and make the wings. Basically, I tried to base it off a target stall speed. So we're trying to glide at around 9 meters per second. So I was figuring, okay, safe stall speed will be, below that. So going with what NACA gives for the coefficient of lifts, and then the maximum angle of attack. The wings are sized at like here, basically, or sorry, yeah, like around here. So basically, we're going for a stall speed of 2 meters to around 2 meters per second slower than the target glide speed for the symmetric wings, and then a good bit lower than that for the non-symmetric wings. Yeah, I probably should have put that in inches squared, but the banana, I don't know. I think the banana's like it's all you need. Anyway, yes.
Yeah, just a comment about the chart. Yeah, I really like the analysis of finding the stall speed. But I think it might have been better illustrated in a graph. Also.
Good idea.
The meters per second, I know you put miles per hour earlier. And yeah, just.
Oh, yeah.
Probably should aim to keep that constant, but.
Okay, yeah, sorry. It is, okay, we probably switched the units around, but it is all the same
Got it.
thing. Yeah, so this, I didn't skip one. No, this is the symmetric airfoil. So here's all the fancy numbers for it. Basically, coefficient of lift and drag for 5 to 10 degrees angle of attack. There's the CAD model of one of the wings, and then the coefficient of lift versus the angle of attack that is given on the NACA website.
Is that surface area, planetform area, or?
Planetform, yeah.
Okay. That's the other reason on it, 'cause I don't know, like 53, like 4 inches squared is meters squared, so it's like between the two graphs, it's hard to.
Yeah, I know, okay, units, we should probably switch that up and make it all the constant, but it is the same thing. So yeah, again, symmetric airfoil used so that during launch, it shouldn't tend to peel away. So this would be the easiest way of doing it. And then I calculated a rate of descent of like about 0.7 feet per second. Realistically, it's probably gonna be a bit faster than that, but that's pretty good. And then also this airfoil we picked because I'd originally picked a thinner one, but then after talking to DBF people, and then also after PDR, we went with a thicker airfoil because it will probably be manufacturable as opposed to the other one, which we'd have a lot of difficulty with actually cutting out. And then this is the non-symmetric airfoil. I basically picked this one because it has a similar size to the other one, thickness wise. And then this one will provide about 2 to 3 times the amount of lift as the non-symmetric one at 5 to 10 degrees angle of attack. And then it should glide a good bit lower, but I basically, they have the same surface area. So we're testing the same size wing, just different airfoil.
Are we building 2 vehicles, each with one of these wings?
No, so one vehicle, I think it's on another slide, yeah, but they're just, you can attach them like modularly. Yeah, and then this is a wind tunnel test matrix that we have, so I didn't want to like put so many words on here, so this is kind of like a general test matrix. So basically we're going to test the symmetric airfoil mounted with thin canards, and then we're going to test like drag, airflow over the wings and the canards, and then lift created with different elevated deflections. And then we're also going to do another test, but we're going to try it with, so the original canard design that I had would be too thin to manufacture, so that would probably just end up being a wedge. But then we also want to make like thicker ones with natural airfoil, but we aren't exactly sure how thin the CNC foam cutter can go. So basically, after talking to DBF and figuring that all out, we're going to make a thicker canard with actual airfoil, but I'm just not sure how that would interfere with the airflow over the main wing. So that's something we want to test in the wind tunnel. And then the wind tunnel test 3 and 4 are basically the same thing as the symmetric airfoil, but with the non-symmetric one. And then the main points that we want to get here are drag and then for the non-symmetric airfoil, lift created at zero angle of attack and seeing if the uh, control surfaces can overcome that, so that when the active stabilization could actually, keep it straight, as opposed to the control surfaces not being enough to overcome the lift during launch.
Quick question.
Yeah.
What, I might have missed it. What's the max speed that you're expecting to see on like the actual flight?
So
To the open rocket, and it shows it.
is it okay?
Yeah, it's on there.
I'm pretty sure it's like 115 feet per second.
That's on ascent.
On a set, okay. Is that
Wait,
what
do you know
you
what-
would be
oh, sorry.
testing in the wind tunnel?
No,
The
I don't think
140
it goes that fast.
No, no, it doesn't. No, it doesn't go that fast.
That was what I was wondering. It's like, how are you gonna test from 50% to 100%? The wind tunnel can't go that fast.
Oh, sorry. For that, that's like 50% to 100% the wind tunnel speed, not our actual speed. And I was just gonna try to, fit a curve to that.
Gotcha. All right. Makes sense. Would you do something to try and like, I don't know, maybe scale up your test model in the wind tunnel so that you can kind of, even at lower, wind speeds, you can still try to get a little bit more information out of it?
What do you mean scale? Like make a bigger model?
Like make a bigger model, like just so you can keep the Reynolds number the same. And like even with the lower wind speed, you can kind of try to get, predict what it's going to be at faster speeds for like a smaller model. If that makes sense.
Well, I don't think we can make it much bigger because the test section of the wind tunnel is not massive.
I think that our rocket will fit in the wind tunnel, and
Yeah.
that's about as big as we can fit in the wind tunnel.
Got it. Okay, that makes sense.
Yeah, because I guess the main question that comes out of like, what is the Reynolds number difference going to be between? Like, are you going to be able to match the Reynolds number and like create flight-like conditions that you're going to expect to see in glide or in flight?
I mean, it's probably not going to be perfect, but I think it's big, I'd get something to
Because,
go
yeah,
off of
that's
at least.
something to know is like what Reynolds number you're going to be running at, and
Mhm.
you're expecting to see in flight, and then what Reynolds number you're actually casting at, so that you can at least see where your discrepancy is going to be.
Okay. Yeah, I was definitely hoping to get some help on the wind tunnel stuff because I've never done that before. And then again, launch test matrix. I realize this is kind of wordy, but data recordings, that's just copy paste all the same thing. So we're gonna do 4 launches, 2 for each wing configuration. And then we're basically just testing launch without active stabilization, and then launch with for the symmetric. And then 2 launches for the non-symmetric airfoil. 1 launch to basically gain some data to see, did the stabilizing work? And then we might need to tweak it, and then we can try again. And then we're gonna record maximum apogee, maximum launch velocity, glide speed, and then like handling feedback and flight time, basically, and then we can compare it to open rocket, and that'll tell us if it's actually being very accurate or not. Then yeah, obviously, oh, sorry, that wasn't up, but obviously, if it crashes, we will rebuild it and then fly again. That's the plan. Yeah, and then brief overview of the other lift surfaces. So the canards were again sized pretty similarly to the old booster. They're about 15% of the size of the wings. And then yeah, this is just saying about what I was saying about manufacturing them. So we're gonna make like just basically a wedge and then one with an airfoil. Vertical stabilizer. So we're not using a rudder. It should just be stable enough on its own. And we don't really think we need yaw control anyways. So the vertical stabilizer is a bit smaller than it was, like ratio wise compared to the old booster. But
What's the biggest risk in not having rudders? Like what risk are you assuming with not having yaw control, and then why is that not an issue?
main issue that I was thinking of was for launch. If it starts to, how do I do this with my hands? Wing, if it peels to the side, they have no control to counteract that. But I'm pretty sure it should just be stable enough on its own.
If open rocket stability calculations are correct.
are correct at all.
So we're assuming that so the rudder control is more of an issue during launch than it is during glide.
Yeah, and then, I mean, a lot of like similar size like RC planes, yes, that's the word. And then there's also there's a website online that makes flyback boosters and similar stuff, but most of them like they never put rudders on them.
Okay.
And then I think some of the old star boosters, because they made a bunch of them, they made some smaller scales, made bigger scales. Half of those didn't have rudders either. And then when we were at PDR, I don't remember who was saying it, but one of the alumni was also saying they don't think we need a rudder. But yeah, for just the glide phase, I don't think it's a problem. And then I also tried to calculate the CG and the aerodynamic center separate from Open Rocket, and it gave me similar numbers. I was mostly calculating it for the flight phase, so I was getting the CG is pretty much where the avionics stack is because that's most of the weight anyways. And then the aerodynamic center is going to be, I think, 1.5 inches aft of that. I didn't put on here, but yeah, so that would be good for flight.
Do not have a large, what's your, what percentage of the master rocket is?
Yeah.
It's like, again, under 300 grams is what we were limited to, so it's pretty. We go from 3.06 pounds to 2.7 pounds, so I don't know what the percentage of that is.
Yeah, yeah, it's not a lot, but
Yeah.
yeah, and then here's just an image of the CAD models of the two wings. I think we have, we have slides going on, but basically it's just, we're making wing mounts, so ignore the servos in here, they're going in the wings, but we're making these fiberglass wing mounts that we're gonna attach to the wing so that we can screw them on. And then, so we picked these servos because they recommended we use metal ones because they said it kept having gear shearing issues during the Old Star booster. So basically, smallest servo that we could find within our price range that had metal gears. And then I also picked them based off of this RC plane servo torque calculator, which for our purposes ended up being all of the servos create way more torque than we would really need. But yeah, and then so we're going to stick them in the wings because that's the easiest way to connect them to the control surfaces. And then Cameron has a model RC plane and it has like a attachment points. I think you're talking about that for the wiring, but that's what we're gonna do that. And then the so the ailerons are about 12% of the size of the wing and the canards are 20% the size of the canards. That's again similar to how the old Star Booster was. And also something we're going to test if that's good or not with the wind tunnel. And then we've already talked about controls a lot, but testing different control systems that Autopilot has to support. And then this is just servo torque calculator. And then basically summary of everything I'm kind of saying with the testing. So overall, to decide from this, decide from our testing. So pick the ideal airfoil and delta wing configuration, optimal control surface sizing and deflection angle for that. And then best control system, and then not on here, but I guess to see how accurate Open Rocket is. And then test the pilot system. Okay. Yes.
The servo.
This.
That's like,
oh, sorry. I don't know. This is basically just a calculation to decide how much torque you need the servo to generate based on your the size of your control surface and how much the control surface will be deflecting and how many degrees the servo will turn. Yes.
Is that 8.5 e -6 just to take the centimeters to the fourth times miles per or centimeters cubed times miles per hour?
Probably, I don't know. I didn't make this. Oops, I can't go at it. I didn't design this equation. Um, but looking at it, probably.
Okay.
So you're citing that, are you citing that based off of launch or based off of flight?
Launch.
Okay, so are we expecting to actually the servos during launch? It doesn't seem like we are, so.
Well, if the active stabilization is going to be
Are we
using.
gonna use, like, or even use the canards? That was kind of assuming we use the canards.
Well, sorry, I'm counting the canards as a control surface.
Oh, okay.
But yeah.
Yeah, the full wing ones might be a little overkill for that,
Yeah.
especially going that fast.
Yes.
Yeah, for the airfoils, I was wondering how you got like the parameters, like lift to drag ratio. For that, yeah, lift coefficient versus angle of attack that provided.
Wait, oh, that chart.
Yeah, and the lift to drag ratio.
Yeah, that's all on the NACA website. They just have that listed automatically for every airfoil. It's basically just coming from Xfoil. Why is it look weird or something?
I was thinking it was the lift to drag ratio seemed a bit high, but.
Yeah, I think
If you do that for like the entire vehicle instead of just the airfoil, perhaps.
no, that's just based on the airfoil, but the entire vehicle, I don't know. But yeah. Well, how does the shuttle fly? That thing just falls. Okay. Other questions? I don't know. Okay, Spencer, your turn.
Okay, so now on to structures recovery. So we start with main body. So just like PDR, we are still making it out of a cardboard tube, common in kind of low class rocket models. It'll be around a 3-inch inner diameter and a 3.1-inch outer diameter. This is just what we're buying off of the internet. So those are their weird dimensions. So it's kind of what we're left with. We're gonna buy like a 3-foot long tube and cut it down to size. So we need to take like around 6 inches or so off the back. And then here we have a picture of kind of the main layout of what it looks like from a top-down view. And you can see kind of where the avionics will sit inside the rocket and where that'll coincide with our wings, and then the canards placed further up. Yeah, and we need to, for our servos, for the canards, we need to put them inside the main body because the wings themselves are too small to fit the servos inside. Versus for our main wings, we're planning on actually putting the servo inside the wing itself.
We know the maximum aerodynamic load that you're gonna see during descent.
That was in Tyler's slide somewhere. That torque calculation was taking into account that number of whatever the max aerodynamic load would be on them. Oh, you're talking about on the whole body?
Yeah, I'm talking about on the body, like, is you're gonna be cutting out a whole bunch of sections, like, do we know that load? Do we know that this craft paper can take this load?
It's says on paper, but it's epoxy impregnated.
Epoxy, yeah.
Like,
All I know is they've used it for a lot bigger rockets than what we're trying to do.
I just figured that out. It could be a simple calculation.
So,
Just
yeah.
taking, dynamic pressure, max load, and figuring out like what stress you're gonna expect to see axially. It's pretty simple calculation.
Okay.
Just kind of a sanity check of like, you're probably gonna get a factor safety of like 30 or something
Okay.
wild. But just making sure that like when you start cutting a bunch of holes in your tube, you're not gonna accidentally knock down your strength and just go.
Yeah, okay.
Stop.
We'll definitely look at that. For our nose cone, it's gonna be around 15.7 centimeters, or just because that's how it's an elliptical shape, just for ease of manufacturing. We're also deciding to put a mount for a camera inside the nose cone itself, since we plan on 3D printing it out of PETG filament. which should be strong enough as well. We need to do a little bit of calculations on that. But as far as we're aware, it will work. And it'll be a lot easier to manufacture with that mount already attached so that we can just slip the camera inside. Total, that'll come around to 80 grams, 5 of which are the camera, so super light run camera that we'll talk about more later. But yeah, we're planning on just making it out. We can, if we need to, make multiple iterations of the design since it's really easy to manufacture. And just kind of test and see. Yeah. Yeah, it could,
That'd be a fun test.
it would be, yeah.
Structure slabs always.
We should.
Yeah, and oh, and also from our camera, we'll be running a wire down the main body tube into the avionics bay to get that live video feed back down to the ground during flight. So for our wings, we are going to use EPS foam because we have that already. So we don't have to buy anything new. And we're reinforcing them with a carbon fiber spar of about a 1/4 inch. Also, we already have, not 100% sure on diameter or dimensions, but we have them around. DBF has a bunch, so we're planning on using some of theirs. And for manufacturing, we are making, as we said, 2 wing designs, and the canards will be the same on both iterations. So we're planning on using their CNC foam cutter to create the profile for those both wings, which to our knowledge should be doable. We did scale up the wings from PDR, so we're gonna cut from a 1 inch thick foam stock down to about 3/4 inches at its maximum width. And yeah, so our wings are going to be attached to the main body with a wing mount that we'll talk about more in the next slide. But we're planning on attaching the spar to that mount itself and then being able to slide the wings on and off for each iteration. As well, we're going to be attaching the servos in the underside of the main wing, kind of in this picture over here. So we're going to run a wire through the side mount and along the bottom of the wing that will just kind of cut out into a little mount for the servo itself in the wing.
I didn't touch that typo, but it's 1.5 stock foam board.
Oh, 1.5.
More
Okay.
room to play with because the hot wire cutter melts quite a bit of the material, so we have more. We need to have more area to play with in the stock.
1.5. Okay, but yeah, what we have already, so it shouldn't be any issue. And for the actual mount itself, so after PDR, we decided to change it to like a fiberglass mount. And what we're planning on doing is taking a 1/8 inch fiberglass sheet and heat forming it to the body of the tube itself to get that nice cut, and then cutting out our shape. We're attaching it with 4 screws into the main body, and then the wing will slide on to this mount itself. So we're going to,
Are you
Yeah.
screwing it in? Like, are you just assuming that you're gonna be able to screw into the tube itself, or you're gonna have like a nut?
we're gonna epoxy nuts onto the inside of the body tube so you can screw into those. So we'll have 4 of those on each side, and then additional for the canard as well. Yes.
Are you planning on cutting it, the fiberglass?
Just cutting it. We also could do
Yeah.
a layup. It would be easier probably if we can't get this cut with a drill.
Mhm.
Also, do we know, is 4 bolts enough?
Um,
Calculate that.
yeah,
Help us.
the wing is very light. I mean, it's all
Yeah,
foam, so it's
not the weight.
but
of
it's
obviously,
the-
they're-
yeah.
And so that's gonna be, so this is gonna be pure shear. I mean, assuming how big are your screws?
6.
And
Yeah,
this
six.
is like, because you're basically gonna take, because basically that you have to figure out like the force that's gonna be, because those 4 bolts are taking all of any aerodynamic loads. So we have the aerodynamic loads-ish that are gonna be on the wing surface, or again, you could just do like the max dynamic pressure over the area that the wing is gonna experience. And assume that to be your force, and then like basically you're just gonna be countering that all in shear.
Okay.
And I think there's shear screw calculators for, like, I'm again,
It would probably.
Probably gonna be fine.
Okay.
like, it's probably gonna be fine. And you're probably gonna be like way over, but like, it could be weird and like, it might not be like, just with the way that it's being loaded, it could like shear, it's not, yeah.
Like, I feel like the cardboard would be the first thing to, give. How would we get numbers on like? Will it rip through the cardboard? Is
Well,
that?
ripping through the cardboard is gonna be complicated. Then you have to do like, if you're to figure out like what's your max stress, like what your stress concentration is around the bolt. I mean, like, you can do some really basic FEA, but like that, I'm not structured.
Okay.
So
So you were worried about the screws shearing?
like if the screws, more like the screws pulling out, like it's
Okay.
gonna be like figuring out like how much preload are you gonna need to actually like retain all that stuff.
I think, yeah, once we get more like exact for how much,
This is
Force.
those states, you can
But-
also just do this.
yeah, I mean,
That was our thing.
wind tunnel, if it breaks
It's one of
apart.
those things that it's like, if it falls off, don't be surprised.
Yeah.
Yeah,
We're gonna lay up the fiberglass on the body tube as like just a rectangle and then let that stack. On the curved rectangle.
We talked about laying it up instead of deforming last night and then it just didn't make it in the slide. Like, what's?
And then have you done sort of like? You know, like how thick you want it to be, because that could also like go into the bulk caps too, if you're worried about like either the screw sharing, or if you're worried about those like little rounded like areas to screw into, like if you're worried about those breaking. I think this would be another thing to consider.
yeah, it'll be 1/8 of an inch fiberglass. And I mean, we can change the mount design. It's just kind of what we settled on. But in terms of manufacturing, it'll be very similar to make a more kind of substantial design, and it won't add too much weight to it in that consideration. Yeah. All right, and then for our avionics bay, which is gonna sit in the middle of the rocket, we're planning on creating like a little hatch almost to be able to access it from the top in case we need to change out stuff. In between both configurations, we need to change out the servo connection in the wings because we're changing the wings itself. So we want access to the avionics bay in case we need to change anything. So what we're planning on doing is having two centering spacers on either side of the avionics bay, which is about 7 inches in length. And those are going to be glued down into the main body tube. They'll fit a pretty exact, and we're just gonna cut them out of like some plywood or something feasible that we can drill in or screw into, something lightweight. Yeah.
Another thing with tolerancing, like.
Yeah.
Don't put 3.0 of not.
Yeah,
I get it.
Yeah. No, we're a lot of our tolerances and sizes are just kind of whatever ends up happening. We don't expect, like with our wings, we're not sure at all like how much is going to be cut off with the foam cutter or like, how much to account for. So we're kind of just waiting to see what happens. And if we need to as well, but yeah, I just did that because it's the same the diameter, but in reality, yes, it should be a bit smaller. And then in one side, we are going to have, that picture is probably wrong. One side, we're gonna have a hole in the bottom here that'll face up towards the nose cone to connect a wire through. And in the back, there won't be that because that will be pushed up right against our engine mount. So we don't need a hole there. And then the main top, what we're gonna do is cut out part of that cardboard on top and screw it in as well with some like washers on top to hold that in, so that we can unscrew it if we need to access the bay or anything like that. Again, we haven't really calculated anything if it'll tear away at all, or like break, but I don't think that should be an issue
This
for
one's
there. Yeah. Cause it's not under, it shouldn't be under that much pressure. Yeah, yeah. And yeah, and then for our motor mount, we're hoping to do, we have our motor itself and the casing that we're gonna be buying online. And we want to make like a little mount itself to slide into, because the motor comes with, and we'll talk about this a little bit more, but it comes with like a casing at the front for a secondary charge that if you wanted to like eject a parachute out of the nose cone or something, you would use, but we don't need that for anything. But it is still part of the casing that we get. So we want to just make a solid tube that we can just slide it into, and put a centering ring around that. So we were hoping that we could 3D print that as well. And so this main tube here and this centering ring would be all one structure that we can just slide in and then lock in. And then this ring here and these, again, like screws or something to hold the motor in just while we're like handling it and stuff. During flight, the pressure should keep it in, but just in case, and during the glide phase, we don't know. I mean, no forces should be acting on it, but just in case.
Which motor are you using?
I think it was in.
It's-
The,
That motor.
Yeah.
Um,
So like, I don't remember, like, is this one of the motors where like, where's the thrust, like, where are you reacting the thrust load from the motor? Like, is that gonna be onto the avionic, like that avionics plate, or are you reacting, or does it have one of the lifts that where it's gonna be out?
It has a nozzle.
No, it's like reacting, it's like where is the force from the engine gonna be actually transferred into the rocket? Like,
Yeah,
is it
there's
on the forward?
Where's the plate?
There's a plate in between the avionics bay.
Yeah.
and it's gonna be.
Okay, but does the motor have like so, like with bigger motors for, Crescendo last year, like that motor, it has a ring on the outside where that's the thrust ring. So that like, you're not actually reacting any thrust load on the forward end of the nozzle, but you're reacting it all through the centering tube itself and then out through your centering rings. So I don't know off the top of my head if that F40 it has one of those rings, or if you're actually going to be reacting it through the avionics bay, because that's going to determine like how strong that bond needs to be, and also how you're going to be able to retain it. Because if it does have that like aft ring, you're not going to be able to like keep those flush, because it'll stick out a little bit.
the screw bits at the end there,
Yeah, do you actually have
those stick out a little bit.
Yeah, but do you have a picture of the motor?
I think it's in the propulsion slide further into the
This is,
action check.
okay. It's somewhere, but I don't think it,
I don't think it has a, what are you talking about?
Yeah.
Thrust ring.
I don't think
I
it,
don't know if they. Out of that, because it's so small.
yeah.
Yeah.
We are planning, like,
It's getting to the.
I know what you're talking about, yeah. It's not Apogee, if you look up F40W-7. you'll find it.
Nope.
You're like,
Oh, because you're just using a 29mm casing.
Yeah.
Oh, okay, so that's one of the ones that we have. So it does have the aft ring.
okay,
I don't know if that's
We have 29.
true though, because it has the little like ejection charge stick out portion. So like, are you saying like we have to cut a hole in our spacer and then stick that through so that the actual like thrust ring is sitting on the spacer?
No. We can go up to the hangar after and I can show you guys what I mean
Okay.
by that. Because we have the casing, but basically what that means is that like, it's better for you guys because it's like, basically you don't need to have a clearance fit. Like, you're not gonna actually, like, the motor doesn't need to touch that the backing plate on the end there.
Okay.
Because no force is actually gonna be going through there. It's
Oh,
actually gonna be reacted through that through the tube itself. And then
Okay.
basically it's just gonna go through the tube and then out through your centering rings and then into the frame of the rocket.
Gotcha.
And so just like keep that in mind for like, it's not gonna, you're not gonna have that flush fit on the back face, on the aft end. Like that motor's gonna stick out a little,
Okay. Thank you.
but we can go up to that.
Okay. Okay. So then, launching, we are still kind of deciding or figuring out where we're gonna actually be launching from. So it's a little up in the air of how we actually launch it. But just one of our ideas is to stick, it on what would be 2 launch rails. We probably only actually need 1. But we want to have, if we're using launch lugs, them on either side of the tube. So we do have 2 of them to account for when we land the plane again. Because depending on where we launch, we could be landing on like a harder pavement. If we land on the grass, it won't be a problem at all. And we'll probably just keep one, be able to launch it straight off the back with 1 rail. But in the case that we do have to land on pavement, we want to have some sort of protection on the bottom to like slow it down and grip.
And also more
surface.
stable.
And yeah, if we're landing on like 1 tube on the bottom, it's gonna roll, and then that pressure is we put on the wings. We would try to avoid that.
Yeah, I would avoid launching off 2 rails.
We don't think we'll launch off 2 rails, but we think like still launching like this one, but still having like
Yeah.
the
like-
2 sides
Yeah,
kind of
maybe-
thing.
Maybe you can just 3D print epoxy on some like skids. or
Yeah,
something
yeah.
like That are it's aerodynamic skids or something, if that's something that you're concerned about. Is the main thing that it's like, if you're launching off of 2 rails, you have any sort of thrust imbalance, then you're gonna start to bind your launch lugs.
Mhm.
And then like, because so then not only that, but then it's hard enough to like line up 2, like if you're gonna have multiple launch lugs, you have to line them up axially and then trying to align like 4 so that they're radially concentric, and then also like aligned axially is going to present a lot of challenge. You can add a lot of friction so that you don't actually reach the velocity that you need, your stable velocity of the rail.
Would
Yeah,
it be, if we had like the 4 launch lugs and just had 2 that we're not using on the other side, would it be stable enough to launch off of 1 rail just on the side? Or should we buy skids and have launch lugs in the center?
Yeah, I would
Easier.
like, if you could potentially like 3D print it, like, and make sure that it's like all, so that you don't have to worry about the alignment. But like, it's easiest to just launch off the one, because the other issue, when you're launching off the, like one that's off to the side, is that like, you're gonna start to have a moment.
Yeah.
So you're gonna start to spin around the tube. You don't want that,
No.
like, that's gonna immediately cause your wings to snap off. So definitely, like, I think one that's axial is gonna be your safest bet there. And like, also you can 3D print all that's,
just
so you can kind of make something that's nice and like formed to the skin, like your wing mounting plate that just has the tube embedded in it.
Okay.
Because that's also gonna make it not fall off as easily if you're landing on the pavement.
The one thing that we were worried about was if we had landing skids, we would need like at least probably 2 on the bottom and 2 up near the canards. How that affects like aerodynamically. I guess it would just have more drag. I don't know if we really care about that, but. Yes.
But
Yeah.
it's at your scale, like, yeah, they
Yeah.
impact it a bit, but it's all like, this is not a high performance vehicle.
Yeah.
Um,
Well, and it doesn't matter because we wouldn't have launch lugs on a booster because it would just be mounted to something else and then that would have the launch lugs.
yeah,
So like, we're not really, this isn't something we really need to test for future vehicles.
well. I guess this brings up a better question, which we can talk about at the end.
Okay.
Like, why are you doing this?
Yeah.
But yeah.
okay. But yeah, that's reason. All right, and then talk about the recovery system a little bit and why we decided to forego the parachute. So from PDR, we originally were thinking that the parachute would have to sit a little bit further up from the back and launch either at the top or bottom of the rocket. Since we couldn't fit anything next to the motor, without offsetting the motor. And we did not want to have to deal with that. So, but after kind of like talking with some people and feedback from PDR, we kind of thought that it might not be super important to have parachute recovery or that like feasible in the first place. As we stated before, like our max altitude is going to be well below 400 feet realistically, and a pretty quick rate of descent. All told, these are under like really ideal conditions, but it'll probably be very fast. So in most scenarios that would be deploying our parachute, we're going to be around 100 to 200 feet above ground. And all these scenarios are ones in which we've lost control of the vehicle. So the deployment time and just the amount of added mass just really don't make sense to do. So instead, we're kind of, again, depending on where we launch, we're hoping to just take shelter, kind of get in like a bunker or something and, clear the area that's not supposed to fly that far away or anything in the event that we do lose control. And for whatever reason, it just keeps gliding. It goes maybe half a mile or something, but it's also, a 3-pound vehicle. So it's not going to do too much damage if it crashes, as long as it's not crashing into people. But there's more like rationale and a little bit more like numbers and stuff that we have on like a separate kind of write-up of why we decided not to include it, that you can find on there. And yeah, I think that's last slide. Ready?
Hello. Thank you, Spencer. And this, I think, is just a picture we talked about already previously, so we can go over a little bit again. That's the propellant there. You can just, it's like a reloadable kit that you can put in and out of your motor casing that we are also buying, or I think we have some in the hangar as well. Yeah. So we can just use one of those, and then we'll just get like 4 or probably 5 of the, in case we need, or one of them's broken, or we like want to do another test or something, get like 5 of the casings. We can just, or 5 of the motors, just load them in the casing and go. And then I'm going to move on to avionics, radio control. None of this has changed since PDR if you were here. So I'll just go over it quickly. We're using this flight controller because it has all the pinouts and stuff that we need for like GPS and airspeed, pitot tube, and all of that are like already preset, and it has within RD the flight control firmware that we're using. It has a profile already in that software to control all those things.
I heard pitot tube. Are you having a pitot tube? Where?
On the wing.
On the wing.
We'll talk about that in one of the slides. So we're just gonna like run it comes with tube. I think there's a picture, and you just run it out of the avionics bay to wherever you're mounting it, and we'll just put it on the wing and make sure it's outside of the whatever that fancy arrow word is. The boundary layer. Yes, thank you. And then here's some wiring diagrams. I just took these from the manual for this thing. We're not going to use all of these, but we have the analog video transmitter. It has pinouts for it. You can just stick it in right here. And then the actual camera can also be put in this here. There is a caveat. We have to make sure that we set the firmware settings to output the right voltage for all these things, which you can do actually from your phone. It has Bluetooth, which is kind of crazy. And then we have a receiver for control that is over ELRS protocol, just easy, like pre-built protocols. I'm turning off. Oh my gosh, Discord, go away. I don't know how to turn that off. Sorry. Good Discord. That I have on my Mac computer, yeah. Okay, and then and there's the USB extender here, just like plugs right in, and you plug it into your computer, and you can load the firmware and change settings and all that. So pretty easy. The idea was ease of use, ease of like being able to access the software. We didn't want to build our own like PCBs and all that, and then have to deal with our own manufacturing issues as well as software issues and all that. We just want to be able to plug and write some code if we need, but mostly just press some buttons and be good to go and trust that it works, or blame somebody else if it doesn't. And then this is the flight software using ArduPilot, mostly because it's really versatile. We can do, like I talked about, add plugins and changes and stuff if we need to, but also because it has good integration with stuff that we want to do for future projects. If in the future we want to try doing like autonomous return of the booster, we can try to do that with Mission Planner, which is developed to work with ArduPilot. And then also, if we want to test stuff, we've been trying to get OpenMCT as a ground control display working for our other rockets, but we could definitely test it here because ArduPilot and Mission Planner have like pretty extensive documentation for how to integrate it with OpenMCT. And we can hopefully do that pretty easily and do some testing of how we want to build solutions for this and then make them adaptable to other projects at CPSS. And these are more like long-term goals, but the reasoning for choosing ArduPilot was because they worked with these two pretty easily. And then here's just a quick components list of all the main like things that we need. I don't know if anybody has any questions about those. I don't think so. And then here's the ground control stuff. I just have one of these and it works with all of these, so we're going to use that. And then this is the OpenTX on here it's just the firmware that puts displays on this little thing. So if we need to like read telemetry of like, oh, I actually want to see like the real airspeed or whatever, you can also with ArduPilot have it display on your video screen too, some of those stuff. But if we lose video, you can then see it here. That's the goal, because hopefully you have longer range on your control than your video. Ideally, yeah. And then this is, yeah, OpenTX I was just talking about, comes with it. And then here's just a quick little schedule that I put together. So I have this set up for, this is our go, no go with the launch weekend being after this. We're not quite certain because we're still in talks with the people that like own the airspace that we would be hopefully launching in. And we don't know when that will happen. We are like emailing back and forth, so we're not quite sure.
So typically a launch readiness review is the go, no go. So like.
We figured we might have issues and then we like
Right.
give ourselves a week.
Yeah, so, but like, that's
Okay.
kind of the thing where it's like, hey, we're coming into this launch readiness review, we have like XYZ issues.
Okay.
Here's our path to resolve them, but like, in coming out of that, we're like, we're still go for launch.
Okay.
So like,
That should be the same
yeah, like typically, like.
for using the nomenclature correctly.
Yeah, cause like,
Okay.
the go, no go, like, you can still make that call, like, anytime before that, but typically, like, in terms of like a launch readiness review, you're saying that, yes, we're ready for launch.
Okay.
Or like, this is our path, like, no, we're not ready now, but
Okay.
this is their path for launch, versus like, or like, if you're no go, then you're like, yeah, we're still like 6 months out or whatever.
Sweet.
So,
We'll change that for the next presentation.
cause like that's,
Yeah, I was wondering if you could go into more detail on your next steps and what you're hoping to present during your launch readiness review.
Yes, so that would be like, yes, we have everything screwed together and based off of our tests, we're sure that like it's not going to fail under the conditions that we assume to be in. And then also like, hopefully we will have like qualified the software is going to work prior to actually physically qualifying the whole rocket. And the idea would be then, okay, we've done wind tunnel tests. We've also like done extensive unit tests and whatnot of the software that like we've developed if we have to do that. And then that would be kind of our qualifications for launch readiness review. And then also like having all of our test safety procedures in place, having those be reviewed by our safety officer who's over there. And make sure that we have like a formal write-up of here's our steps for the launch readiness review. Here's our steps for how to change out the wings that we have written up. Everything is all formalized.
Yeah, and so typically also for the launch readiness review, your range is gonna be involved, so whoever like. Like, I don't remember, are you gonna be doing it at Paso or?
We're talking with them. We're not sure.
Okay, it's like.
when or how that works, yeah.
Whoever like is gonna be like your range operator, like who's gonna be kind of overseeing this launch, they should.
Yes.
Be invited to the
Yeah.
launch readiness review, and because basically, like, they should be go, and then like they're gonna have the final say on like, especially with procedures and
Yeah.
making sure that basically like. You're good to go for launch.
So this is very tentative. I'm assuming that we're gonna email back and forth with them, and then they're gonna say like, in order to develop the procedures, we're gonna need a couple more months.
Yeah.
And we'll probably either like maybe do a launch ourselves at some field somewhere in a park, because it's small enough that we could do that, and that was the whole goal. I don't know if the school would be okay with us doing it on one of these fields, but we could ask.
Like C-class motor.
Okay, yeah.
Like,
With
so,
Air 121. I haven't looked at the FAA regulations in a while.
We are in
but
controlled airspace due to
The
the
airport.
airport, but
But I think.
We can
that,
ask
like, I think the height requirement, there's like some height limit
Yeah.
that you can.
I think we're right on the edge. Like as soon as you go into Poly Canyon, you're no longer in.
so our
Yeah,
grade.
technically it doesn't hit campus.
Are you sure?
Yeah, the delta is like 4.5 miles radial. Pretty sure we're outside. of it.
Okay, I thought I looked at a map for like, can I fly drone here? And it was like up to Poly Canyon.
I was in drone. I was in drone.
Okay. So maybe we're good to fly it here. We just would have to ask Marshall, and maybe President Armstrong would say no. I don't know.
Yeah, so like I would talk about, we were talking with the tourist, so she has experience.
Okay.
Getting clearance because she used to do that.
Okay.
She used to have a little project that she
Yeah.
would fly out there with little motors.
Okay.
As long as you don't fly them into people's cars, you'll be fine.
Sure. And I would be okay with flying it into my own car for science. I think that would be
Yeah.
fine. Just to see how it affects the,
But I feel like there's enough large fields.
Sure.
The Madons.
yeah, I agree.
If we launch it from the Bishop's Peak, what are the repercussions?
We're doing an environmental study. Yeah.
From the launch
Yeah.
point, or is it 400 feet from, so like, where's?
It's from sea level. I think it's from the launch point. That's a great question. though. I'm sure they have regulations on how high you can launch it from. I'm sure that that's in there. I think I read something.
Yeah, overall final comments, like, I think you guys have a lot of great content. Like the test matrix stuff, I was very impressed with the wind tunnel test and the testing procedures. I think, like Will mentioned as a joke, that throwing it off of Bishops, even Dan mentioned it.
Oh, yeah, absolutely. Yeah.
During PBR, but I think like that would be a valuable test to.
Yeah.
Because I know you guys are testing in the wind tunnel and doing the launch tests, but. Doing the test about the vehicle in flight during its like flight phase. I think that would be a valuable test.
I agree.
Something like that. And then I think one big thing I was hoping to see during this design review, but one thing that needs to, or I think should happen for the launch readiness review is having more of a trajectory analysis and modeling that flight path.
Okay.
So like having graphs that would, model the velocity. Or like anticipated velocity or altitude and time.
Sure.
Yeah, throughout your like test or whatever you're hoping to.
Okay.
Flight profile you're hoping to follow.
Fair enough.
Just as a suggestion, building off of the throwing it and seeing how it glides, the side of the arrow hanger facing that field has a wonderful drop off.
True. Can we get up there?
I've been up there.
Okay. You'll have to show us how to do that.
Yeah. You just gotta open a few gates that aren't locked.
Okay.
They're not locked.
Okay.
They're not locked.
We're not gonna do that for safety reasons.
For safety reasons. So.
We just
People let us go.
go up the side of the hill. There's nothing saying we can't.
Yeah.
Yeah, I think throwing it off of a hill is probably the best option, unless there's a building we can throw it off somewhere. Baker, maybe. Yeah.
Looks great as a test article. I think
Okay.
I think you have a lot of analysis done, and I think a lot of your testing, but it's like. There's a lot of, like you're saying, a lot of manufacturing tolerances, like your, like propulsion analysis, like all that's kind of like. Because it's kind of small and it's like dinky and huge margins on everything. So you're kind of like past the point of analysis, which is in.
So I think as well. Start throwing it.
Like that. Because this seems like all the stuff that's like great between the PDR and the CDR for like a big rocket. They're like, hey,
Sure.
we're doing all this stuff because we don't know.
Yeah.
We don't know what wings we're gonna use. We don't know like how we're gonna control the rocket. We don't know how it's gonna handle in flight. But these are things that you need to like learn by flying something.
Yeah.
And that's what this is. So this is a test article.
Yeah.
Like this isn't like a fully fledged
That's the goal, yeah.
idea.
Yep.
So it's like you can take a lot more risk of like, do we really know how this is gonna handle?
Yep.
Yeah, don't like, and you're never gonna be able to analyze it.
Yeah.
So just,
Well, and the idea too with this one is that we keep it around as, yeah, a test platform. And maybe we like, don't like any of these wings. So next year we test a couple more. Or like we build a bigger rocket and it doesn't fly the way we want to. So we can test other things on this because it's modular. We can slap things on it,
Yeah.
change how it looks, throw it off a building, get more data.
All right, then this, but if you were to talk about what the plan is for next year and what. This is the test, so like next year,
Yep.
you build a full scale, like huge one, or are you gonna
Big.
keep getting?
Yes, build bigger. And we may not do full size, like we don't know exactly what size, we don't know what payload we're gonna be trying to move. Obviously, the idea is like over the summer, once we have next year's projects for the club figured out, we would have like a more good idea of how much weight do we actually need to deliver to what height? How big should we then start building boosters to test at that size? Right now, the like two main ideas of what we would be trying to deliver to what height would be like, we're building a liquid lander and we don't want to like have it go up. We just want to have it go down. So we put boosters on it, get it up, have it just do the down part. Or we're building like a Carmen line and we want to like just have funny boosters on it. And so we do that instead.
It could also, just as an idea for next year, there are points if your launch vehicle returns back to the launch site. So
Yes,
that-
yeah, FAR has extra points for this kind of stuff too. Yeah.
that's like looking at like, because I think that's the big thing of like, because once you have a platform, like right now, there's no driving requirements for
Yeah.
full scale. And so
No.
that's gonna be the biggest thing. Find those-
And we're not quite sure like what our projects will shake out to be next year in general. That would be cool as well. Yeah. And we have like industry friends that do that kind of thing that we could talk to and get advice. So there's different ways we could go with it. Again, this year we're just building a test article, test platform for different ideas. And the idea would be that no matter what we want to put it on, we have experience flying something similar. Yep. Any other questions? Oh, here's the budget. This is all the stuff that like needs to go into it. This is all the stuff that we need to buy. We own a lot of these things, or DBF has stuff that they're willing to donate. And there's just like screws and hardware everywhere. And yes. And then we are under budget. I forgot to put on here, but I think we're about $40 under budget. If we're using a motor mount from the hangar that would work, then we're $140 under budget. So looking good on the budget. Yeah. And then we might, with all that extra money, just buy more motor propellant kits so we can do more tests. And more fire, more explosion. Yeah. Thank you to our sponsors. Thank you, everybody, for coming online. Good to see you. Okay. We love you, Josh. We miss you.